Oops. Yeah, yeah, I can write bigger, except where's the eraser? There it is, there it is. All right, good. So, yeah, last time I talked at great length about this Hamiltonian. And so now the topic of today is I'm going to explain how to generalize the non-invertible duality, the Kramers-Wanier duality of the Ising model to other models. And the key we'll see is topology. Not obvious why in what I said before it has anything whatsoever to do with topology. But so I could just start today with the topology and then go back and explain what it has to do with Ising, but I thought it would be better to sort of keep going along these lines and generalize Ising, this Hamiltonian, to some other things. And as usual, when you're generalizing things, the key is to invent tricks that help you do it. And the way here, that's the way forward, at least I think the easiest way to generalize this is to rewrite in terms of projectors. So Fiona was talking about writing certain Hamiltonians there. In fact, because in some cases, you can get exact ground states via, because it's a sum of projectors, and so projectors square, so operators that square to themselves. So the point is, this thing can only have eigenvalues 1 or 0. And so if Hamiltonian is a sum of projectors with positive coefficients, well, then if you can find something annihilated by all of the projectors, if your Hamiltonian is a sum of projectors with positive coefficients, then you can find something annihilated by all the projectors has energy 0, but that's the lowest possible energy. So you can get that at ground states. That's what, at the very end last time when I talked about these exact ground states in this deformed model, that's how that works. So that's not so much the tack we're going to take today, although that little fact I said. But it still turns out to be exceptionally useful to do this in terms of projectors. So let's do this for Ising. And so notice, if you take any Pauli matrix, so including X, and I square that, well, because Pauli matrices square to 1, this is twice itself. But then, in fact, a few more seconds, and you notice that this thing squares to twice itself. Okay, so this is the way to write Ising models, projectors. So I'm going to define now operators. So I'll just call it E, K, and then I'm going to use the notation from last time to make it uniform. If you remember, this thing was H2J minus 1, and this thing was H2J, each of which squares to 1. And so if I define this operator, it's not quite a projector. Up to a normalization, it's a projector. There's a good reason for that what looks like a funny normalization here that you'll see in a second. Okay? So then, the Ising Hamiltonian is just H equals square root of 2 times t. Again, the 2 is funny, but so it goes. All right, so far I've done, it's complete trivia. I just rewrote these things in terms of projectors. But if you recall from last time, I made a big deal about that these H's satisfied the bond algebra. In particular, well, they square to 1, so I won't write that down again, but the key thing was that HK plus 1 anti-commute, and then the other ones further away commute. So now you can ask, well, I wrote this linear combination. They don't anti-commute anymore. But what happens, and you can just check, excellent exercise for the student or anybody interested, is that the following relations hold. That's a relations because plus or minus 1, this is true. So that's happens. It just muck it out and use that relation and the fact that h squares to 1, and there you go. So it's actually, in some ways, simpler. So that it's a little bit funnier. It's not a commutation relation. It's another one. And then you also check that, you check this one. That's obvious. And then, like I said, they commute further apart. Okay, so it's another algebra, but this is a super important algebra, and that's why I did this. This is called the temporally-Lieb algebra. The Lieb is Elliott Lieb, the mathematical physics great. Temporally, maybe you haven't heard of, but he was a stat mech great, and he died not that long ago. He lived till 100 or something. So good. Elliott is still writing papers at age greater than 90, so this shows that people who do statistical mechanics have longer lifespans, I think, is the moral of that. So they wrote this fantastic paper in 71 on models of this algebra. And the reason why this algebra is interesting, obviously, the way I introduced it, it's just a way of rewriting this free fermion bond algebra. But this is a much more general thing. So the temporally Lieb algebra now, so let me do this by erasure, is just the fact that now you put a parameter here, which I'll call D. And so Ising is D equals square root of 2. All right, so it's a parameter, but why they did this in this masterpiece of a paper was that lots of models can be written in the same form. Of the TL generators. Well, and that satisfy this algebra. Again, so there's 3 kinds of relations. There's this one, and this one. All right. So lots of models. So what happens now, so again, you make the same kind of arguments that I made with the bond algebra. I made a big show to say, well, I compute the spectrum of model 1, that was model 1, and then I wrote down this dual model 2, the H hat. I said with appropriate identifications of parameters, then the spectra is exactly the same. So for temporally Lieb, the situation is a little subtler. First of all, because we got a parameter now in the algebra. So you have to match the parameter if there's any going to be kind of thing. And then there's more stuff with boundary conditions and all that. And it's certainly not free fermion. So these models are interacting and all that. So it's a much more elaborate story. But from the point of view of the dualities that I'm discussing, it's exactly the same. And so there's sort of 2 things you can think to do. So sorry, let me list some models with the temporally Lieb algebra. So the most famous one you've probably all heard of is the XXE spin chain. I'm actually not going to talk about that at all, but I thought I would mention it. It's a little more complicated, but if you can ask me about it, there are things you can say. No, only to get criticality. It could be anything you want. No. Nope. I mean, in a particular examples, you'll find like nice sets of examples where they're taken. No, XXE, it's anything. The catch in XXE, I will just say this, you don't have to know this, is boundary conditions, or to get the boundary conditions to work, you have to do funny things. So that's why XXE is peculiar from the temporally Lieb point of view. It's useful. One that I will explain momentarily is the Q-state POTS model. So I'll explain that. And then another one it's an old model, but it was renamed to be the golden chain. And in fact, in general, so what Eduardo was referring to was saying, don't you have to take discrete values? And there's certain things called anion chains, and those happen at certain specific values of this parameter D. Because again, and things vary. Yeah. So there's lots of stuff, but all these have temporal Lieb algebra and all these equivalents. In fact, okay, I'll tell you one of the, you will see in the literature the word equivalent. Oh, well, the XXZ chain at a certain parameter D, you identify with Q in a particular way. And, well, we'll see what the D is for the Q-state Potts model, and then the models are equivalent. They're not quite equivalent, and there's all these subtleties, but they have lots of things in common, and sometimes including the non-invertible defect. So one thing is, so we can use the non-invertible defects sometimes. To map between such models. And there's an old word for that Hermann knows, since he literally wrote the book on it, coming up in the quantum group language. This is, in essence, what they called in the old days an intertwiner. I'm not going to really talk about that in my lectures, but I thought I should mention that. And another thing is you can do use the temporally Lieb algebra via the thing I will describe to find these non-invertible symmetries. And a more refined version of the dualities that so I mean, this is where we're going today. Hopefully today I'll get through most of how this all works. Next time then I'll give applications, some of the marvelous applications of these things. So yeah, good. Any questions on the things? Yeah. Sorry, I can't hear you. The second. Sorry, which? Oh, book. Hermann Sierra's book on quantum group algebra. Oh, yeah, sorry. Yeah, a book by Gomez and Sierra on quantum groups algebras. So something, again, I will not talk about. Yeah, sorry. I was advertising Hermann's work. This book's from a long time ago, the 90s or something, yeah. So anyway, there was a whole huge story in the 80s about quantum groups and lattice models. Fascinating story, all sorts of amazing things were learned. It turns out there's a lot of structure to quantum group algebras that we don't need for what I'm going to talk about. And so I'm not going to talk, so I'm not going to bring this up, but it's important. So this sort of thing, I'll make maybe a few other comments there, but there's this whole vast literature on this, a lot of which is very relevant. But I think it's fair to say that now via the fusion categories that I will describe later today, for the things involving these non-invertible symmetries and that sort of thing, all you need is the fusion category. You don't need all this quantum group stuff, but it's great stuff. Good. Any other questions before I start to get more concrete? Okay. So before again I get abstract into this fusion category, I'll just show you that it's not that hard to generalize this. So actually, I'll leave that and I'll do erasure. And so again, yeah. Sorry, 1 sec. Let me just erase that. Yep. Sorry, I didn't hear most of what you said. You're asking about quantum group algebras. I heard that bit. Oh. Fusion categories are a more general thing. But one way of getting fusion categories is from quantum group algebras. Yeah, good. No, thank you. That's a good clarification. But I would say fusion categories are more general objects, but when you go to a quantum group, then there's all this other stuff you can do. So they're more, in a way, they're more refined objects. That maybe is a better way of saying it. Yeah, thank you. No, that's a good question. Right. So what I'm going to do is generalize this to Q-state Potts model. So what we do here, okay, so notice this term, remember, flips, and this measures nearest neighbors. And so notice if we write out the E2J, well, this was 1 plus sigma x j. I guess in this normalization now, 1 over square root of 2. Right, well, just write this thing as a matrix. Right, it's a 2 by on one site. So on one site, this thing is just a matrix. Well, 1 over square root of 2 times that. Right? 1 plus sigma x. So just ignore the j in x. So let me just write sort of, well, I'll put it here, but then, okay? So now the Q-state Potts model, you say, well, you take the Potts model, you take the Ising model, instead of having 2 states per site, so Potts, you have Q states per site. And then for our generalization of E, you take kind of the obvious thing. You take 1 over square root of Q, and then you have one, just the matrix with all ones in Q with Q by Q. Right? And then you can see in a second, we'll call this E. Maybe I'll put a Q there for a moment just to remind you that's the Q state version. So E Q squared equals square root of Q EQ. Right? I haven't done this one yet, but I'll get it to a sec. Okay? So we've just got a Q state system and this thing. And you know, so if you, okay, you can always subtract the identity, and you let me get away with something here. There was some constant there. So you can always subtract the identity. And so what this is doing is just takes any one state to any other state. It's perfectly good Hamiltonian. It's what the Ising is doing, just there's just 2 states. I want to leave, yeah, good. Let's kill this. And leave these. All right, good. So this thing, now, so this just measures. So if we now, okay, so let's do this over here. So if we do 1 plus sigma Cj, j plus 1 with 1 over square root of 2, which is the E for Ising. Well, what this does now is it gives you a square root of 2 if the 2 spins are same. And 0 if not. So for Q states, we then do the obvious thing again. We say 1 over, we then just take, so this was E sub 2j. So for the Q version of E2j, we take this to be Q. If they're the same, of the Q, and then different. So it's obvious again, both of these satisfy this with D equals square root of Q. So that's obvious. What's not obvious, but takes a little while to show, not that hard, but it's a little work, is it satisfies this as well. That's why the funny square roots of Q, because then there's no coefficients here. Okay, so we found this is actually what Temperley and Lieb did. They didn't say it this way, but that's what they did. They did for the full classical model. Okay, so I just wanted to do this. So there's another model with Q. And in fact, you'll see in the literature frequently people referring to the Q state Potts model with Q not integer. And what they mean by that, I'll give you a precise thing in a second, but what they mean by that is basically they write the generators in terms of the Temperley-Lieb algebra. So the Q state Potts Hamiltonian, I would write as HQ equals, well, T times as j equals 1 to L, E2j plus j equals 1, L minus 1, E, oh, that's 2j minus 1, that's E2j. So they write the model like that, where the temporally Lieb generators, and then you say, once you write it like that, if all you're doing is manipulating the algebra, well, Q is just a number. So they will say it's the Q-state Potts model. It obviously isn't. It's a model you get by this, but you'll see that often in the literature anyway, and that's what they mean. Is it the same as what? Yeah, no, that's why I'm going to do the loops next. Yeah. Well, that's really, well, one way of doing. That is one way. Okay, so good. Now I'll try and give you a precise thing, and this is how we're going to get topology into the story. So there's another marvelous thing you can do, which is sort of done in Temperley and Lieb's paper. They didn't say it the way I'm about to say it. But then there's a paper later in the 70s, so I'm just trying to give credit to all these people who understood all these amazing things. There's a paper by Baxter, Calland. So Baxter is the StatMech monster. I mean, just incredible result. Wu is Fred Wu of people from the old days know who that was. I don't know who Calland was. Anyway, from like 76, where they more or less did what I'm saying. They said it in a different way, but this is what they did. Yeah. No, everything I'm going to talk about is finite dimensional. So there's finite dimensional. No, so that's this Eduardo question. Right, if you want arbitrary Q, then you're going to have to go to infinite dimension, right, or this topological thing I'm doing. There's discrete values, just to jump ahead, and for those people who know some CFT, no fusion categories, for values of Q equals 4 cosine squared pi over K plus 2, and K integer, K a positive integer. Then there's finite dimensional versions of this. Actually, you can put another parameter there. But anyway, and these are lattice versions of the minimal models of conformal field theory. But anyway, that was a tangential comment, but some people in here probably know these things. Okay, so what I'm going to talk now about the loop model presentation of Temperley Lieb. Yeah. If what groups are really? Yeah. Yes. And yeah. Well, so you can do that, but even in just the original context. So the answer, one answer is that the right structure is not groups, it's fusion categories. And the other answer, but if you like groups, you can do these things for non-abelian groups. People in the StatMech language, in the field theory language, people know what an orbifold is. So you can do an orbifold by a non-abelian group, but what it secretly tends to amount to is you mod out, you pick abelian subgroups and then mod out sort of do that. But then you can prove that, no matter how you do that, you get the same answer. So it's a cheat, but it works. That's a good question. I don't know. There might be some people here who know that. I don't know if they've we would have to. We haven't got to fusion categories yet, but I want to say there's thousands of mathematicians who have studied these things in excruciating depth. So it's conceivable one of them has proved a theorem of when it works and when it doesn't, and I don't know what the answer. Or it's conceivable to do, but I don't know the answer to that question. Good. Any more questions before I get a little more abstract? Yeah. No, the cheat is the cheat is, like I say, you do abelian subgroups. People say that's not what we're doing. I've never been convinced that what they're really doing at the end of the day is, I think, just picking, anyway. But that's a subtle question, and I'm certainly not going to get anywhere near it, this talks. Yeah, right, so, yeah, let me spend, I was going to come back to that, but no, but this, actually, I meant to, and then I jumped to that. So let's hold that for a second. So let me explain because it's only a few minutes anyway, so good. So let me explain that now. So just hold that, that's going to happen, but not, okay, good, I can kill this. Well, I can kill kind of any of this, to be honest. Yeah, so we have this Hamiltonian here that, as Horacio just said, looks exactly I wrote it deliberately so it would look exactly the same as the Ising thing. And again, we can go through the same arguments. So if it only depends on the temporally Lieb algebra, well, then it doesn't matter, which one we put here and which one we put there. So we can define a model 2 where model 2 comes from the flips, the things I just erased. So this is now the Potts Hamiltonian schematically. So this one is flip, or shift, I should say. Plus this is, ask the question, are nearest neighbors same or different? So this is my schematic. Potts Hamiltonian. But as far as the temporally Lieb algebra goes, they behave exactly the same, right? There's no even odd distinction in this. So you can run through exactly the same arguments I went last time, so I won't do that. And you get the same sort of duality. And in fact, people in the literature, I see. And so again, you get this phase diagram where we have T over J, and you get a phase where there's order, and there's disorder, and there's a point in between that's the self-dual point, and it's a transition. So one thing already that's different is you learn, and in fact Temperley and Lieb learned this in their original paper. If Q is greater than 4, it's a first order transition. So this does not, none of the things I just said follow automatically. So this is more analysis work, and it's not, the model is not free fermion, you really have to work. But the way they did this is because they knew it was temporally Lieb, it was the same as the XXE spin chain, and then they knew what the answer was for XXE spin chain. And that's how they knew this fact that it's not critical. But anyway, all right, so that picture again looks exactly the same. I emphasize it's a result that this is one point. So I'm just going to say this for a second, just to show you there's other examples. There are other examples where something happens in between. You get what's called incommensurate phases. If I take this Potts model and I make it chiral, which I can do. So just to say, people write this down and they say, oh, well, it's obviously the transition is at the self-dual point. That is not always true. It's the most obvious candidate for the transition. In the cases I just described, it is the transition point, but it is not obvious. And so even in the example I gave you, it's not always critical. And there's examples where that's not true. The clock model, yeah, these chiral clock models, yeah, they have to be. No, not for the temporally Lieb ones. For more general models, yes. Yeah, for the temporally Lieb ones, it's still, yeah, temporally, that's right. Right, so now the defect story. So again, there's this duality that maps T hat equals J. Literally everything I wrote down last time, just look at what I did last time. Exactly the same arguments. And then the thing is, well, what's the defect? So there's a defect. And again, you can get this by hand. I don't know if anyone ever wrote out in the literature. Somebody must have. We wrote it out in my paper with Dave and Roger, but someone must have done this before. And if you remember, we had a weight. So I drew it like this. So where this was model 2, and this was model 1, or in our new language, the model and its dual. And so remember, we did the weights sort of as this product there. So we had W 1/2, 1, and it was a weight between this and that. W 1 3/2, a weight between this. So hopefully this is all familiar. Again, it's the exact same thing as I wrote last time. But then in this case, what you find is W of this way is 1 over, remember we had this stupid 1/4 thing, so it's Q to the 1/4 instead of 2 to the 1/4. And then we get, so that's an omega, not a W, AB, where the two spins, these Q state spins, are A and B, where A and B are running from, say, 1 to Q. But then the slight catch when you work this out is the other one is the other. Oh, and I didn't say what omega is, but I'll say that in a second. Minus AB. So AB running from 1 to Q, and omega is Q through to unity. So that's what you find. Yeah. Yeah. Yeah, so there's Q-twisted boundary condition. So if Euclidean icing, a very important boundary condition is twisted, which means you basically say, you pretend when the interaction is going around the world. So it's like periodic, but then you twist. When you say on one site, well, pretend, so if we have up-down, pretend it's really like up-up. You change the Boltzmann, you flip the Boltzmann weights instead of saying up-down is up-down. Well, so with Q states, you can then do analogs of that. Yeah. Oh, no, it's not the same. Yeah. There are connections, but yeah, it's more complicated. Good. Okay, so then this goes through, oops, what's this? That's there. So omega's the Q through to unity. This just, again, depends on the two values of the thing. You just check it. And again, so we have this Hamiltonian. It changes this thing. So I'll erase this now. And then the only difference, so you go through the D. So this defines D. So this is the dq. And so then you see dq dagger equals not just 1 plus flip, but you get 1 plus, I'll tell you sort of the shift operator. Where this one shifts all spins by 1. Cyclically. A. Okay. So people call this, including me, call this Kramer-Swiney duality, but it actually really isn't. Remember, it's a natural generalization. I think this was the original reason people started studying Potts models in the 50s. Someone said, well, can we concoct a model that has this duality? Another fact that maybe a few people know in here, but not many, so I'll say it. Turns out around the same time in the early 50s, this brilliant mathematician named Bill Tutt invented something called the Tutt polynomial. And one of the reasons he invented, there were a couple, was precisely because it had two parameters, and when you interchanged the two, it gave you the same value, at least on a planar graph. So it was a polynomial associated with a given graph. So the graph is our space-time. And so literally he defines this object. It's still called the Tut polynomial, and it is identical to the partition function of the classical Potts model. So you can look on Wikipedia, and you see the different definitions of the Tut polynomial, and one of them is the Potts model partition function. So anyway, so duality in all these cases was the reason this model started, one of the key reasons why this model, because it has this nice property. And then, okay, so temporally Lieb came along later and did that. So this trick now, so this concludes this kind of, it's not a dumb trick, it's a beautiful trick where we write the terms like this. In the models that I'm going to discuss, there's nothing like that. That's not the dualities. And this is why Eduardo said, you know, people tried for many years to generalize these in various ways, and you kind of run out of gas. You can come up with lots of variations on this theme, like the Potts ones. But all of them are kind of the same, more or less the same. So there's some differences here. But they're more or less the same. And anyway, so you have to do something much more high-powered in order to get somewhere, and that's what I'm going to do. Good. Oh, right. So now I'm going to go to the loops, but yeah, go. Yeah. 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 Despite my long friendship and collaboration with Eduardo, why it works is because he thinks of things in terms of gauge theories and I don't. So feel free to translate if this helps you. And I think this is part of the issue. You know, I do things my way, and string theorists do it theirs. But you know, so this is a good thing. I mean, I don't think in terms of gauge theory. But right, you're gauging the ZQ. Yeah. Yeah, yeah.
So in that perspective, duality means two different dualities. One is the Hodge duality, the duality of forms,
Yeah.
which is what generalizes to higher dimensions. And the other is a duality of groups, which is only possible for ability.
Yep.
The groups, the representations of all groups. For the non-abelian case, that's what it is.
Yeah. Well, right. But okay. But my answer to that, yes, I agree completely. Yeah. Yeah. And I think if you can, here's one sentence that will summarize all 3 lectures of my thing is that rewriting lattice models in terms of fusion categories gives you the right structure to generalize such dualities. And so people foundered about for a long, I should say foundered, they learned tons of things, you know, rewriting this way, writing it that way. And I'm telling you the correct way to write it if this is what you're interested in. There are other things in the universe. I know. No, the story's not over, but yes, I agree. For 1 + 1 dimensions, this is the correct way to do it. And people have already learned a lot about higher dimensions because now we understand 1 + 1 very well. Okay. So this is now going to look totally different. So probably for the rest of today, maybe I'll get back to spins at the end, but we're gonna be talking about pictures and topology. So it's going to look utterly, completely different, except, well, okay, I'll make contact with some of the words I've said before. But it seems like it almost seems like I'm starting a different story. I could have started my lectures with this, but then I would have to introduce the spins, which would seem to have nothing to do with what we said before, and also have no contact. So the generators are the temporally Lieb, and so by generators, I mean the EJ. So say this here, of temporally Lieb, act on strands. And by strands, I mean you take a bunch of lines like this that we number 1 to, well, I'm going to number them 1 to L, but already, well, you'll see in a second, this is sort of half the length of what we did before, and that hopefully will be clear. And so what I'm going to write now, the E sub j, does the following on strands. So this is the jth strand, and this is the j plus 1th strand. So these are a bunch of strands, and when I act with E, so say this is E2, what it does is fuses those two together and then recreates two new ones. Okay, and then we can do this, say, and do that. So this would be 4, 5. So far I'm just drawing pictures. But okay, so what this is in terms of temporally, so it's a presentation. The word presentation is a broader word than representation. It means I'm writing down this algebra in a different way. In physics, presentation usually means different model. I'm just going to write down this algebra in a different way. And here's how I'm writing it. I say I take this. So this particular thing I wrote out, well, I guess the lowest one would be E4. And then I act with E2. And then with E3. And so this is the picture version of this. And notice, so why it's loops is because these are never intersecting. Sorry, what? Yeah, so there's just definition, right. So, I mean, I could put JJ plus 1, but the convention is just right that way. No, all right, so it's acting on this tensor, so you can think of it as acting as a tensor product, just like in a usual Hilbert spin space, you tensor together all the strands. So now we're tensoring together all the strands, and it acts like this. That's all. Yeah, if you remember the EJs, well, right. So some of the EJs I wrote before do and some don't, which is part of what I was saying vaguely that, this trick is kind of a weird one. When you put it in a more general setting, that trick where you do, sort of half looks one way and half looks the other is different. So now, basically from now on, except when I go back and talk about icing or pots, we're just going to think of this as some uniform model, not, there's not some even odd. Yeah, exactly. So you can think of this as just some model with spins on every site. Maybe there's some rules, and we'll get to that. They're on every site, and then we do this. We're not quite there yet. In fact, the spins are going to live on the other ones, but anyway. Good, yeah, please ask. I mean, I've totally shifted gears here, so we'll come back, I promise. I still got time. Where are we today? All right, so I'm halfway today, and then we got another lecture tomorrow. Or another lecture Thursday. Okay, so now, how do we, I said this is we want to act on strands. So we want the temporally Lieb algebra acting on strands. And so the way to get the temporally Lieb algebra is to make the following rules. So we say now, okay, we identify, so the two rules we identify configurations, and let's not use configurations, let's use pictures. And I'll give you examples of both of those in a second. So topologically equivalent means I can deform one to the other without cutting or doing anything like that. And 2, closed loops are removed, so it's not quite identified, but you have to multiply by a weight. So what I'm really doing, so to be precise mathematically, I'm considering the vector space of all strands combined with all possible strands combined with the E equals that, all these. And so each one of those is a separate element of this vector space. And so when I say, but I identify anything that's topologically equivalent, and then I can remove any closed loop, but I multiply the element of that vector space by D. So the pictures now, so let's see what let's write out temporally. Okay, we don't need this. We do need this. All right, so this relation, the first one, is the top relation, which says that if I take two E's, so multiplication, like I indicated, is stacking. So if I have EJ, so this is the J plus one strand, so that's EJ. But then I do EJ again, well, I do that. So I just stack the two on top of each other. And I just said, by definition, I can then get rid of that. So I identify the two things in this big space of all the pictures I can draw, this big vector space. So I identify the two, but then the catch is I have to multiply that element of the vector space by D. So that's how I realize the first temporally leap relation. Now the second one is cool, and this is why the funny square root here, because it keeps me topological. So I'm going to do, I've got room here. So I'm going to do, first, I got to use three strands, because I got EK plus 1, or I guess I did J. But. So we got EK. All right, so then this one looks like this. But now so this is EK. But then I do an EK plus 1. This is EK plus 1. But then I do an EK again. Let me just erase those. Do EK again. Right? And you see, topologically, I can just deform this back. This equals that. Topologically. So this is what topology has to do with all this. So that's the temporally leap algebra. Historically, the way it came out, so there was I should have mentioned, the earlier work by Fortuyn and Castelline that came up with the classical Potts model had this nice graphical way of rewriting. It's called the cluster expansion sometimes. And then the surrounding loops of the cluster things are this, and then Baxter, Kalend, and Wu kind of put all these ingredients, temporally leap and all that together to give you what I'm saying now. Baxter, Kalend, and Wu didn't say it the way I'm saying it, but it's all there. Nope. I mean, these things, you can construct a solution Yang-Baxter from this, one of the... Yeah, so I can define R matrices that satisfy Yang-Baxter. But I'm not going to use any of that this time. It's related, but I'm not using any of it. Good. Yeah. Well, they give right. So, okay, good. I'll make that comment now. So Javier asked about rating. Yeah, so what happened historically, it's one of these, all these brilliant people doing stuff. And so already the bizarre thing, so I mentioned a second ago, Fortuyn and Castelline did this graphical thing. That paper was in 71, the same year that temporally leap. So it took 5 years for people kind of to sort out all the connections between the two. So in the 80s, Jones I forget which, the first paper was 83, but I think the one where he made the connection was 84 between, defined the knot polynomial, the famous invariant of knots and links, called the Jones polynomial. So, and the Temperley-Lieb algebra is the underlying thing. So again, this is going to take me far afield. Ask me in the questions if you want to hear a little more. But you get the Jones polynomial from this Temperley-Lieb algebra. You write, so again, this is a tangent, but for people who are interesting, you write this, something like this, the overcrossing, and then the undercrossing. So it's totally tangential, but very cool. My conventions are not normal. It's probably a minus, but anyway. Something like that. It's called skein relations. But anyway, you project your knot onto the plane, you get overcrossings and undercrossings, and then every time you replace this, you do that. So that's the Jones polynomial. There's one important subtlety having to do with the writhe that I explained. But in essence, what we had here, it says, Jones says you project it onto the plane, on a plane, you replace the overcrossings and undercrossings with this linear combination, and then you do this, exactly this. You identify things that are topologically equivalent, but then get rid of closed loops with a weight d. And if it's a link where everything's closed, that's just d to some power, and that's the Jones polynomial in d. Or polynomial in Q, which, oh, sorry, yeah, I should say D is Q plus Q inverse or something like that. Again, something like that. Those conventions, that's wrong as written, but something like that. No, that's not it. Well, this is Jones's result. This is one Jones of Fields medal, what I just butchered here. So I butchered it, but... Not for this case, no. So in Jones being, well, a great mathematician and human being, was honest. And so, in fact, he wrote his paper. He had literally this algebra. Maybe his normalization was different. But he had literally this algebra. And this mathematician, Dye Evans, who some of you know, told Vaughan, by the way, Temperley and Lieb had this algebra. So as opposed to some people who would have said, well, I co-invented it, so I'm going to not acknowledge that, and then they'll name it after me. Acknowledge the Temperley and Lieb. And then quickly after that, again, people understood how to use lattice models to make new knot invariants. So there's this whole big boom in the 80s. So for this thing, no, this is the answer. I mean, up to conventions. This is the only way of doing it. Now, for more general fusion categories, there's ways of doing it, but the fusion categories I'm going to talk about, actually, so I'm going to start in a few minutes, are more general than things, because they don't have to have braiding, is the answer. So yeah, I've kind of jumped ahead. To answer your question, I jumped ahead, but maybe that was useful. Yeah. Sometimes people call Temperley-Jones. That seems to have died out again, but if you look at some of the papers post-Jones, people said that, which in a way is kind of fair. I mean, they were doing completely different things, and yeah. But anyway, yes. But sometimes it was Temperley-Jones algebra, but that seems to have died out again. Nobody does that anymore. Well, maybe they should. He deserves it. Good. Any more questions? Okay, so let's step back for a second and just say what I was doing. So I went to these lattice models. I talked about bond algebras. I then, introduced these Potts models that satisfied this more general algebra called the Temperley-Lieb algebra. Then, once you go to this realm, you find this now has connections to topology and knot theory and all this stuff. So these are old. I mean, so this is from the 80s, and lots of stuff happened in the 80s. And then it kind of died out. Died out in the physics community. Sorry, not in the math community. Died out in the physics community, all these connections. And there was a remarkable paper, though, coming in, which people, again, quickly realized. So Witten wrote a famous paper connecting this knot theory things to Chern-Simons theory. And then, I don't remember, everyone may remember, who were the first, people recognized quickly that this Chern-Simons theory had something to do with rational conformal field theories. And I forget exactly who did what in what order. What? Was Witten who recognized, well, there's Valindes, did the Valinde? No. Ask me when I'm not being recorded what I think of that paper. That was not the first person to do that. Jones had done that years before. But the connection I was about to make, that's crucial for this, that somebody did invent something. There's a spectacular series of papers by Moore and Seiberg, and I think 89, and maybe went on for a year. And so these papers were on rational conformal field theory. Okay, and it came out of all that whole Chern-Simons-Jones polynomial story, but they recognized, again, clearly the same kind of math, this stuff, was going on there. And so I guess, well, since I drew the braiding, let's say why. So in conformal field theory, we've got a bunch of operators, chiral operators, and you want to know, say, what happens when I move one around each other. Well, if I think of this moving around in time, so this is two-dimensional, but I add another thing. This is exactly like a braid in space, in this extra fictitious time. So all this math, they all of a sudden recognized had something to do with rational conformal field theory. So that's a great story. There's some lectures that they gave back in '89. It's not on archive because the figures were hand-drawn or something, but you can find them on what's called Lectures on RCFT. And what the mathematical object they invented, there were some antecedents in the math literature, but I think they really crystallized what was going on. They're called fusion categories. So that's the structure that describes this. So this is a slightly more general object than the thing you did, because this braiding that I drew to answer Javier's question, I don't need. So the things I'm going to tell you about for the rest of this time are more general objects. And again, that's right, Hermann was asking before what they have to do with quantum groups. Well, so quantum groups give lots of nice examples of fusion categories, but again, they're more general objects. Less refined, but more general. Okay, so, and the reason I'm doing this, because it's not that hard to teach you what these are, but what this will do is the following. It's really a miracle. So you can then define these models, these spin models, say, like Ising, Potts, and I mentioned briefly this golden chain, and many, many more. In terms of, sorry, I'll go down here. People can still read. In terms of data from the fusion category, people can still read that, yep. I'm going to tell you what the data is. But this is some mathematical object. It's all sorts of interesting stuff. And you can define these spin models in terms of it. You say, well, okay, well, fine, we can define lots of things. But the payoff is enormous. And what you get, I'll capitalize it for free. It's automatic. Once you define the lattice models in a certain way, you get these non-invertible symmetries and dualities. So in particular, it gives you an explicit expression for the D's I talked about last time. And in fact, it gives you a bunch of them. I'll explain precisely how that is. So that's why we're doing this. And you know, there's an adage, no such thing as a free lunch. This is as close as it gets in physics. Literally, all you do is rewrite these lattice models, and every lattice model I've described before, you can write in this language. And then out pops stuff. You don't have to do anything else. It's just there. People have been defining these lattice models again since the 80s, but nobody until, well, I'll tell you the paper that I think first really non-trivially recognized how to generalize it. Okay? So that's the strategy, and so that's why you have to bear with me. But fusion categories are really cool anyway, so do that. Sorry, so how much time do I have? Okay, about a little less than a half hour. Good, perfect. I will definitely get through what a fusion category is. So good. So another thing, so even if you don't care about lattice models, I'm teaching you something, first about topology and not polynomials. I'm teaching you about something that many mathematicians still work on. So Moore and Seiberg wrote their paper. They were doing conformal field theory. And in our typical physics fashion, you know, the moment someone does something profound, it kind of killed the problem. Because then there was no low-hanging fruit anymore. They kind of sucked up all the low-hanging fruit that people had done. All of a sudden was pretty obvious, and then even more complicated stuff you could do with that. So of course, we, the physics community, responded by going and working on something else. But the mathematicians took this up. So since then, there's been all this stuff. So there's textbooks written about it on fusion categories, and then there's all these generalizations. Braided fusion category, blah, 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 spherical, lots of stuff. But I'm going to tell you about one particular really use of these. So they're called fusion categories. You shouldn't be scared. I remember when I was first learning this, I was frightened of the word category, and various mathematicians held my hand and talked soothingly to me and told me it's really not that bad. So I'm going to try and pass on. They did this for me. I will try to do this for you. to say, actually, not only is it not bad, but it's really beautiful. And then at least in my case, I was sort of embarrassed as it took me so long to learn how to do this. So what fusion categories are good for? Well, they're good for lots of things, but what for this talk, or these talks, they're good for is the following. And this is what's going to let us do that. Okay, so the two key words I will explain to you, that might sound scary, fusion diagram. All right, so a fusion diagram is a labeled trivalent graph. So for example, so there's a trivalent vertex. I don't know, you draw it. All right, so that's a trivalent graph. Let's do a closed one. So you can generalize, but we'll stick with that. And then I just label them. And I'll of course tell you where the labels come from, but at the moment, it's just a labeled trivalent graph. Okay. That's a labeled trivalent graph. And I'll call it a fusion diagram. I think I invented that word, called a fusion diagram. It's good. Okay, so, and then an isotopy invariant is just a number Yeah, sorry, I'm going to explain. It's a number. I'm erasing and talking at the same time, especially after we've been talking for an hour, is difficult. An isotopy invariant, I'm going to tell you what it is. It's a fancy word for, it's basically a topological invariant, but like I talked about a minute ago, but it just means it's a number. So this is the iso invariant. The other thing I mentioned is a number independent sorry, I should say depending only on the topology of the diagram and the labels. So it's like a not invariant, if you know what a not invariant is. But the catch is because we got the labels, that's why it's isotopy and not topological. That's all those words mean. So hopefully not scary. Just something, so in other words, if I stretch this picture, I would get the same thing. So that's why it's topological. So again, this so far, it seems like I've gone a million miles from what I spent the first lecture and the first part of this lecture talking about. But the thing well, now I just erased, but the key is, again, with these lattice models, you can write them in terms of these fusion categories, and then you get the topological defects for free. Okay, so like I say, these generalize the notion of the Jones polynomial and not invariance. And the generalization is because you don't have this braiding that I mentioned briefly before. And again, it started with Moore and Seiberg's work. Okay, so the data. So this is what you need to define a fusion category. It's just stunning how, to me, how beautifully this stuff works out. And so here's the data. So you need a list of objects. So categories have objects, but don't need to know that. A list of objects, and I'll give you examples of this, alpha, beta, gamma. So these are the things that are obviously going to label the things. So you get some list of things. And to give a physics example, well, let me write down the next one, and then I'll give a very obvious physics example that probably everybody knows. And then you have these objects, and you have a fusion algebra, which says you take these objects, and you can tensor them with each other. And then you get a sum over other objects times some numbers times the object gamma. So what these things are these are numbers, these are non-negative integers. So I think probably everyone in this room, it's funny, when I give this talk to physicists, what I'm about to say is completely obvious. When I give it to mathematicians, I get lots of blank stares, but let's see if there's any mathematicians here, if you blank stare. But this is when we're doing tensor product of representations of Lie algebras. So for example, I took that to be 0. 1/2 would be the physics labeling for these objects. And I tensor 1/2 with 1/2, I get 0 plus 1. So the only slight caveat, I've been a little thing here, to be a fusion category, this needs to be finite. As far as I'm concerned for what we're doing, that's just a technical thing because that's what the mathematicians do. A really interesting open question is, well, can we consider situations? And this might be a case where physicists can lead the way because we can ignore rigor for a moment, just see if we can get this to work and then let the mathematicians sort out whether, how this fits in. But they require, to be a fusion category, this list has to be thing. So that's why it can't be you can't just do SL2 for this because this goes on forever. You can keep fusing these and get higher and higher spins. You can do quantum group algebras too, which sometimes truncate. Or finite groups. Yeah, finite groups is a little bit too simple for what we want, but yes, that works. I can see a finite non-abelian group, yeah. That's right. Yeah. Sorry, what? Read the good book. Quantum groups have certain properties of representation. So if you take, there's a parameter in a quantum group called Q, and if Q is a root of unity, it has representations where you can, where higher spins decompose in terms of lower spins. One of the many remarkable features why you can write a whole book, well, and then some on them. Yeah. So that's why, again, they're very naturally connected, which I'm not going to talk about. But yeah, it's really cool. Okay, all right, so one other technical thing. So let me just say 1A, one of these object is the identity, which we will call 1, not 0. Sometimes people call it 0, but I'm calling it 1. And then such that n alpha 1 beta equals delta alpha beta. So when you fuse with the identity, you just get back what you had to begin with. Okay, so the third thing you need, now here's where it gets, so that's definition. You got this algebra, a bunch of objects and algebra, and I'll give you examples, so don't worry if this seems too abstract. So with each object, you have a number d alpha. For each object, and this is called the quantum dimension. Right. That's right. That's right.
Apart of that, are there examples with discrete, for example, with discrete set of elements that have infinite number of elements and are not represented in a group? Or, it's a matter of just...
Yeah, it's a good question. So the question was, are there examples that have infinite number, but they don't just come obviously from groups like they're certainly there's things that come from like super groups and things like that, which are super interesting. So these graded Lie algebras, like from graded Lie algebras, that's a little bit more general than you said. So there almost certainly are, but I honestly don't know if anyone's discussed it, because mathematicians like physicists tend to herd, and everyone I think is happy with that because there's still lots of interesting questions that they can do. But yeah, Herman may know. What? Yeah, but it ought to give an example of that. But for irrational CFTs, I don't think people have constructed the F symbols and all that. They presumably exist. Yes, so that's why I said presumably irrational CFTs, or at least some of them. That's why I meant these super group, or the graded Lie algebra ones are examples of irrational CFTs that are very interesting. But I think it's a basic question. Can you even construct F symbols? And that's not obvious that they even exist. I haven't told you what the F symbol. Anyway, what I'm about to tell you next, does it exist? Does it solve the? Anyway, yeah, I can say it in a second. Right. So almost certainly yes, they do. And if there may be work that shows that they look like them, but I think mathematicians, that's nasty for them, because you're throwing out key things, and they don't like to just babble on like we physicists are happy to do. Yeah. Yeah, but I'll give you. Yeah. But let me give an example that I bet. Yeah. But let me give an example of an irrational CFT that almost certain I would be stunned if it works. Liouville theory. If you could show that what I'm about to tell you works for Liouville theory, this would be fantastic. But it may, but I don't think anybody's shown it. All right, so let me finish the definition though before we. So another set of numbers. Called F symbols, and I will show you with the pictures in a second what the F symbols do. They relate, I'll just say what they do. They relate different fusion diagrams I think I've killed off this pen. Yeah, the blue really shows up well, doesn't it? Without changing the isotopy invariant. Okay, so that's the data. And now, of course, I'm going to explain what the thing. Is the alarm going to go off at 15, Eduardo? Or? Okay. It's important to keep my phone in my pocket so I get the step count today. Right. Good, so I have 15 minutes, so I can totally get through. Ooh, I should have kept that. What? I erased the diagram, that's okay. That's too hard. That diagram is too hard. I'm going to do simpler diagrams. Yeah. Yeah, no, that's true. I should have left it, but anyway. But here's a simpler diagram. All right, so now let me explain what those things mean. All right, so No, that's something more complicated. All right, so let's for my remaining 10 minutes, let's be mathematicians, and then I promise you next time I come back to the physics. But please ask. Yeah. Yeah. Thank you. Right. No, right. So, okay, I'm cheating. I've oversimplified. So in fact, in what I'm about to, I was about to say this. So in what I'm about to do now is, so what happens in these fusion pictures, so for every vertex, so now what this has to do, when n, alpha, beta, gamma, when n, alpha, beta, gamma, so when n, alpha, beta, gamma equals 1, I have a vertex like that. If I wish to make alpha, beta, if I wish this to be 2, which happens, for example, for quantum SL3, then I have to put an additional degree of freedom there. Not going to do that. The last question said, well, yeah, you have to say that, so I didn't say I was defining these rigorously, but another thing I'm inventing is actually the notion generalizes to putting arrows on there, but not today. We'll talk, and I think there's words, I'm doing spherical, something other, there's words in the category line. So this is oversimplified, but captures, I think, all the key features. So okay, so when I'm drawing these pictures, I can have a vertex, so these are the labeled lines in the thing from that picture. Yeah, I shouldn't have erased, but so it goes. But now here, so what these numbers, d alpha, do is, when I take now, so let me introduce one word. So evaluation, so the word they use and I'll use, of the diagram, so this, etc. Evaluation gives you this isotropy invariant. So I don't have to write down the isotropy invariant. So that means the evaluate means you take your diagram and then you spit this number out. And that's called the evaluation. So the rules now, the rules now that I say the number, if I have a loop, a closed loop labeled by alpha, when I evaluate it, I'm turning it into a number, I get d alpha. Now hopefully, glad I got to this, remember, I don't know, half hour ago when I said I was doing temporally Lieb, I took the thing. So now I've generalized that temporally Lieb thing to just something with a label. It says I get a closed loop, I throw it away, but then I get this number d alpha, the quantum dimension. So that's from number 3. And so then these F symbols, so this is what the F symbols do. If I have a subgraph where it takes two things, where I've got something like this, and let me get my correct, sorry, I want to conform to my conventions, otherwise I will completely confuse everything. Okay, so this is just a portion of this bigger fusion diagram, like this. And what it says now, what I'm allowed to do is replace it. So in my bigger graph, I take this, and I'll give you an example in a sec. I take that bit, any bit I have like that, and I replace it with this bit. There's a sum here. I gotta want to. So if you wish, in field theory, it's called crossing symmetry, or SC duality. But I'm saying, when I have a bit of a diagram that looks like this, I can replace it with a linear combination of bits that look like that. And then what the F symbols are these things that tell you how to do this. So they're the coefficients. So these are like Clebsch-Gordon coefficients. Yeah, that's right. I said that for physicists. They're akin to Clebsch-Gordon coefficients. Okay, 6J, I guess, right? I think, yeah, 6J. Sometimes physicists, our notation is embarrassing. No, that's one. So these are 6J symbols, or well, the fusion category analog of 6J symbols. Okay, so let me do an example to illustrate that last point there. So in other words, say I want to evaluate a graph that looks like this. So we'll go alpha, beta, gamma, such that n alpha, beta, gamma is not vanishing. So I can evaluate that. So that's equal to the evaluation. But then I can look at this part. I'll use for this. So I sort of take this subgraph. So I just sort of look at that region there. And then that looks exactly like I drew there. So I can then replace this with the evaluation of this thing. And then I'm running out of time, so much more time do I have? Okay, 5 minutes. Okay, so yeah, oh, good. Then I can write down a few more rules. And so by doing these moves, and I'll give a little more detail in a second. By doing these moves, you just take your complicated diagram, and then you just do these moves over and over again. You get sums of diagrams. Oops, so I lost. You get sums of diagrams, but then I keep doing now, and I eventually reduce them to just a bunch of loops, and then I know it's just d alpha for each loop. So this is the isotopy invariant. So I haven't quite told you enough to make it obvious that you could always reduce it to loops, but I'll tell you a little more in a second. Okay, so is the strategy clear? And then the last few minutes, I'll just tell you one or two more things about how this all works. But before I tell you a little more detail, just say, so this is obviously, this looks incredibly complicated. So you can easily check, this is what Moore and Seiberg said, well, for this to be consistent, you have to satisfy all sorts of things. If you've heard of what the pentagon equation is, that came up in Moore and Seiberg saying these F symbols have to satisfy certain identities, because I can start with this complicated graph, and I could first, use the F move on that bit, and then I can do, that bit and so on, but I can do this in any order, and it's not at all obvious that there's values of this F that give you the same answer no matter how I do it. But the miracle, I think it's just stunning, the miracle is that there are many examples. I say quantum groups give you one way of getting them, but not the only. And d alpha that satisfy these consistency conditions. And so I say it comes from things like the pentagon equation. And so for what I'm doing, so let me just, I can stop, let me write down just something quick, and then this will be a good starting point for next time. Again, where's the thing? Let me just leave this here. So for example, you see quickly when you're trying to solve these equations, some things have to happen. And one of the things that happen, if I have a subgraph that looks like this, where that's alpha, let me do it there. Then what happens, I can reduce this. Again, if this weren't true, nothing would be consistent. Then you see this has to be delta alpha epsilon times d beta d alpha, d gamma over d alpha times alpha. So in other words, I can remove this bubble, and then I multiply those numbers. And there's other ones, but maybe I'll just start out writing them next time. But the upshot is, again, so let me just reiterate the global point, and this is what I'll use next time. By writing the lattice models, these spin models in terms of these categories, and I'll explain how to do that next time, you get these, you can then define these defects, well, topological defects, that give you these non-invertible symmetries. And I will explain that next time. Good, thanks. Oh, I'm sorry. Thank you. Yeah. Yep. Yeah, so excitations then so it's the Hamiltonian is in terms of these things. So then you ask, well, how to make excitations. And so again, in a given Hamiltonian, there's lots of ways, but this gives you sort of a nice basis for the excitations. And again, so if you now want to think, it's easier to imagine in 2+1 dimensions, so this is not exactly the same, but where you have strings attaching these things, ends. So this gives you a framework to define these things, and then also then tells you, for example, in the rational conformal field theory, what happens when you bring these things around. So I'm not going to make a bold statement like, all the operators are given in terms of these things. And in fact, that's not quite true when you do this on the lattice, but it gives you a subset of the interesting operators, say in a CF. So if you pick a lattice model that turns into a conformal field theory in the limit, and obviously you don't have to be that case, then you get really nice ways of defining some, but not all of the operators in the CFT. Right, so next time, if I have time, I'm going to tell you, it's great, well, any on the models are one way of thinking about it, but this is more general than that. No, in fact, I'll tell you, one of my aims next time is to get to some applications of these things. And one of the applications is, so you can now, so you can generalize this notion to think of topological defects, what I just said a minute ago. So using these topological operators, you can make defect lines. And then a Dane twist, for those of you who don't know, is what happens, say you have a cylinder or a torus, and let's say you cut open a torus around one of the cycles, you twist the thing and then glue it back again. And topologically, that's the same, and if you know something about topology. But this, we know from John Carty's classic work on conformal field theory, is a really good thing to do in conformal field theory. Well, we can do this on the lattice and in the presence of these defects. So not only can you do it, but you compute the eigenvalues of the Dane twist, and they give you exact results for the scaling dimensions of operators in the theory. So I'm going to explain that next time, but it's obvious. Yeah. Yeah. Are they canonically what? Well, so what, okay, so the question is, is it canonical or this fusion diagram? So what's canonical is the following. So fusion diagram, so first of all, you have to first pick your category, okay? And because you have to do that before you draw your diagram, because the diagram is labeled by things in the category. So you pick your category, and then you write down whatever diagram you want, as long as it's trivalent vertices. And then, it spits out a number. Now, I can pick a different category and define the diagram. So, and obviously you can pick categories that maybe have similar, so it's gone, the same fusion algebra. So just the fusion algebra, this alpha tensor with beta gives you n, sum over n, gamma. So you can have different categories that have the same fusion algebra. So in other words, you get the diagram, the same diagrams are there, and then you'll get different answers for the isotopy invariant. So the point is, once you pick the category, then everything else, then you're done. But for different, and it's just like with knot polynomials. I mean, you take the same knot, and there's Jones and Alexander and blah, 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 all these, invariance, and just for these things, you get different things, but it's different invariance. So it's just different invariance for the same picture. So is that what you meant by canonical, or? No. So right. So what I wrote here is the only right. So there's no. It is rigid, meaning if you want something that satisfies these consistency conditions, like the Pentagon equation, this is guaranteed to happen. And where the D's are your categories. Again, so if you look in a different model, of course the D's will be different and you get a different number. But once you've picked the category you like, your favorite, whatever category you want to use, no ambiguity. There's literally no ambiguity. Yeah, good point to make. Yeah. Yes. Right. Yeah, that was to motivate, but that's our canonical example. So yeah. So right, because Temperley, as you note, doesn't have any intersections, but I'll explain how that happens. I think I've now already said I'm going to explain next time about 6 hours worth of material. So so you can lobby me between now and then for whatever your favorite thing is for me to talk about. I will be more schematic, I think, next time. But anyway, hopefully gave you enough to understand. Yeah. Thank you.